Right, so today we are going to do something kind of different. Not that different, it's just going to be another playing with an IC. But we're going to use this one, and this one's kind of neat. So I've got some heavy items on the table that may come into play later on. So this is another CMOS chip. It's in the 4000 series, and the thing about the 4000 series, you might think, wow, they must all have some sort of order. They must start off like at the low numbers and then go up higher, and so the early ones must have some importance and be like the important ones. And so we're going to the important ones. They are important. We're going to look at, believe it or not, here's here, it's an HEF, so it's a Philips branded CMOS 4000 chip. So it's not a 4000 series, it's an actual 4000 chip, which is neat. So most people will normally start with the 4001. So I'm quite interested in this one here. I really struggled to find a use for it, as you're going to see. So this is it right here. It's going to come out nice and close. You can't see it, the writing on it, so you have to just trust me on this. So going to my trusty CMOS cookbook by Dan Lancaster, let's just find out what a 4000 is. So it's actually in this book, which is good, even though the business card is right here. So you think it starts on the 4001. 4001, which we haven't done yet, is a 2-input NOR gate, which is very similar to the 2-input NAND gate. But the 4000 is a dual 3-input NOR gate plus an inverter, which, to be honest, seems a little strange, especially when I'm looking at this now. Like, I don't see why it couldn't have been 3 NOR gates. 3-input NOR gates instead of 2 plus an inverter, or at least you could have made the inverter into a, because they've got these 2 non-connected pins over here, you see. So I'll bring that up a bit closer and you can see. So it's got these NOR gates. I didn't actually write down what a NOR gate was, which is what I was supposed to do. But basically a NOR gate, an OR gate. So I am actually going to have to draw this somewhere, aren't I? I can't get away with doing this. I didn't plan this out. I did draw something on a piece of paper, but not what I was supposed to. I'm just going to get this. Alright, so we're going to go here, and we're going to take a piece of paper here. So I think that's how you draw them. I'm just going to double check that I've been drawing these things correctly. So an OR gate is drawn like so. So if you have 2 inputs, 1 and 2, and then an output, basically if either of these are high voltages, the output is high. So that's what it means by OR. So if this is high, then the output is high, and or if this is high, the output is high. So they both can be high, or one of them can be high and one of them can be low, and you get a high output. But if they're both low, you get a low output. But in this case here, we've got a NOR gate, which was the opposite way around. So in this case here, if either of these are high, or both of them are high, the output is low. And if both of them are low, the output is high. So it's another one of these universal gates. Apparently there's a number of them, but the ones that make sense, that are vaguely easy to use, are the NAND gates and the NOR gates. And they're universal, I guess, because they've got like this part here, but they've also got an inverting phase. You really need an inverter in there somewhere to get a universal gate out of it. Universal just means we can make any other kind of logical gate thing out of this. So in our case, we've got these 3-input NOR gates. So in this case here, we can throw in another one. So that's number 3. You can't really see this. But if any of these is high, the output is low. The only way that the output will be high is if every single input is low. So we're going to go with that, and we're going to try and come up with something to use this IC for. And I came up with this thing here. Well, let's just put this on the table first. First off, we're going to get this out of the container. I don't know how this video is actually going to go, because I honestly think it's going to be terribly boring. Because I love these little. I love the fact that this comes with a specially designed container. The older one, I've got a number like these, but they come in these nice little pre-packaged container things. maybe you went and bought them from the shop like this, because I don't know how old this is. This is 76, so this was made in 1976, in the 39th week of 1976, so this is actually older than I am. So maybe it doesn't work. I was going to get out my IC tester, which would go through and hopefully say this is a 4000 series. I can't get it out that way, so you have to press it this way. So I was going the right way in the first place. Out you get, and hopefully the legs will be nice and the right size. I'm worried I'm going to ruin this now. I do have a couple other ones, but they're not very easy to get, these things, so you don't really want to ruin it. And I just wonder, like, why is this the 4000? This is the very first numbered one, right? So you'd kind of think it was the flagship model. I'm just going to just have a look at the picture in the book again to make sure that I have it the way around that I want. So I want it to look like it does in the book, upside down for me. So the notch is over there, and we're going to put this. I don't know where I'm going to put this, because I don't know how complicated this ridiculously silly idea for a circuit is going to. Oh, I can't even fit this in. I hope I haven't statically destroyed it or something. I'm a bit worried about this, right? Because, like, my understanding is that the early series. Oh, I suppose it'll be fine. Oh my goodness, I can't get this in. I can't get it in the thing. I'm going to break it. Okay, I'm just going to have to squeeze it with my fingers. So, I don't know where this video is going to go, if it's going to be me squeezing the side of things. Alright, so we'll keep that for later. But anyway, before I actually get my book out and knock the camera, so this is going to be the idea. So we have one of the NOR gates here, the triple NOR gates, and another triple NOR gate here, and we've got the inverter here. So I don't know if I got the circuit the right way around. So here we have a pull down resistor and 5 volts going into here. So if I press this button, this will be high voltage going in here, but otherwise it's a low voltage going into here. And over here I have another thing. This is just going to be I'm basically trying to make a burglar alarm system. And this one here is, if I press this button, the alarm should go off. That's the plan. So we're going to get to why that's true in a second. This is going to be the reset button over here. So this is the reset button. I'm going to color that one green, because I happen to have the green felt tip pen right here. And we have another pull something way resistor here. Basically, so let's just say the output for here is high. Wait, have I got this the right way around? No, I have, right. So this will be high most of the time. If all of the inputs here are low, this will be high. And so this little LED, this is meant to be an LED. I didn't actually draw the little extra bits. So this is the LED. So if everything is fine, nothing's happening, the idea is this LED will be on, and it will go through that. That's the current limiting resistor over there. Then that will go through this thing here. So this will be high. That will go through the inverter, and that will be low. This is my buzzer thing. So I've got one of these little buzzers. I don't know how that's going to work, because I couldn't plug it in the way I wanted to. I was supposed to get one of those little tiny ones out, but I don't know where I put them. And so that one's going to go to ground, and so I don't think actually driving this through a inverter through a CMOS thing is a very good idea. So we might actually have to do it with a transistor. I'm probably just going to do it with another LED. So for today we won't use the buzzer, because it was a silly idea. I should have got a little small one, but I didn't. And so that goes through there. But so this is high, this is low. Low is going into there, so that's fine. So we've got two lows going into there. So high through here becomes low, goes into here, becomes low. And you're going to see why I have this loop in a second. We'll come back to this button in a minute. But let's just, and then we've got this little complicated thing over here. But we'll forget this for now. We'll pretend that this is always low on this one here. Then say I accidentally press this button here. This will go high. This one will go high. And then the output will go low, because one of these, if any one of these is high, the output will be low. So that will go low. This LED will go off. and this one, the output will become high, the buzzer will go on, and then this ball will become high. And that's the idea is that if you accidentally trip the alarm, then the whole thing just goes on and stays on. So even if you let go of the button, and this goes down to be a low voltage, low input, this is now pulling it up to be a high input. So we're going to have this state where it's latched on, and the buzzer's going on, and the alarm's going off, and we're like, oh no, someone pressed the button. And this one here is the reset button. So because we have this weakly pulled, this thing's in the way, but if I pull this, I think I may have got these the wrong way around. I actually kind of feel that this should go across to there, and that should not have a line there. So that makes more sense, right? Yeah, it does. So then that you've got this pulled, this is being weakly pulled towards the output of this thing. But if I push this button, it will pull this down to low again. So, and if it's pulled down to low, and we're not having any alarm conditions, then this will go to high, that will go to low, and the alarm will go off. So this is my reset button. So we've just made a RS latch thing. And then to make it interesting, we're sort of using this as a reverse or inverse logic. How much time have I spent? Oh, ages, right. This is the inverse logic section. So over here, what have we got over here? We have got the other NOR gate. So by default, these are all pulled to low. I kind of wanted it the other way around. Oh yeah, no, by default these are pulled to low, and so the output of this will be, I think I've done this wrong, haven't I? Yeah, so if I pull these to low, the output will be high. But if I pull any of these high, the output will go low. That's right. This is what I want. Okay. So by default, you can't really. This is meant to be me pulling. These are pull down resistors to ground. So the output will be high, and then it will go into here. So this will be high, and this will turn this whole alarm thing on. Right, so the idea for these buttons are all meant to be pushed down. So these are my triggers. So I want them all to be pushed down, and it's only when one of them is not pushed down, then we have, so hold on. When one of these buttons is not pushed down, then this output goes low, or high. I think that's right. No, what have I done wrong? Alright, so output high with all of these low. One of these is high, then the output will be low. So I made a very strange thing here, right? So in this case here, we have a special alarm where you have to be holding where if none of the things are held down, the alarm goes off. But if at least one of them is held down, the alarm won't go off, which is kind of not what I wanted to do, but it's a silly circuit anyhow. And so that's kind of what I wanted. But hopefully that makes a little bit of sense. I'm just going to go check on something, so I'm going to finish the video right here and make this a two-parter, and we're going to come back and then we're going to build the circuit. So hopefully that made a little bit of sense, and we're going to come back and work on HEF4000. So thanks for watching, and tune in next time.